I will show you one of the important reasons why we want to look at this, at these response functions in the frequency domain. In order to do that, I make two small changes. First of all, I drop the minus sign. The minus sign here is important if you want to calculate the polarizability, because this is the alpha-beta component of a frequency-dependent polarizability. But let's look now just at some response function. And I get rid of the minus sign right now here. First small change. Now it's minus the polarizability. I mean, just some other response function. Then I want to rewrite that denominator a bit. I want to rewrite that I change those around, and then I should get a minus sign here. And if I do the same here, there was a minus there. If I do the same here, like this. What is this now? Because now we can see what it really is. This is the difference in energy between the ground state and one of the excited states of the molecule, because we are right now exact states. So these are really excited states of a molecule. So this is actually an electronic excitation energy. This is the difference in energy between ground state and the excited state. So what I'm standing down here is the difference between the energy of the incoming wave. Remember, I mean, we're looking at the perturbation of a molecule by an electromagnetic radiation of frequency omega, and that's actually not a frequency, but it's the angular speed. The frequency would be nu times h, but it's h bar times omega. So there's a 2 pi in there. Anyway, this is the frequency of the incoming wave, so that's the energy of the incoming wave minus the excitation energy. So if the frequency of the incoming wave, and therefore the energy of the incoming wave, the energy of the incoming photons, which they fit exactly to the excitation energy, I get a transition. When I do that in an experiment, that's like a get transition. I excite the molecule. If I would do that here, I get 0 in here. And here, if it sort of would be minus the frequency, I would get 0. So I get 0 here. I get what is called a pole, because this is a function. I mean, this is a function. This response function is a function of the frequency of the electromagnetic radiation. So there are values of the frequency for which that response function has a singularity, a pole. That you could say that's not very nice, but it's actually very important because they have a physical meaning. That frequency is an excitation energy. So if you want to know what are the excitation energies of your molecule, you can consider your response function as sort of a radio, where an old-fashioned radio where you turn. And you turn and you tune the frequencies, and at some frequency you get very nice music. You get the excited states. The first one, the second one. If you keep on tuning, you get all the excited. Every time you get a pole or a singularity, you know, oh, I've hit an excited state. So in addition to calculating some properties like a frequency-dependent polarizability, which is the value of the response function, all the poles of the response function or singularities, they correspond to the excitation energies. So I get two kinds of information out of that. I can get the properties and I can get the excitation energies. Which sort of shows that this is a very central quantity for if you are interested in properties. And Remember, you can't measure absolute energies of molecules. You can measure changes in energies. And if you're interested in spectroscopy, you can measure the difference between the ground state and the excited state, because that's precisely the energy of the where you have an absorption. Now this response function can give us that information directly. We actually don't have to go via a separate calculation on a ground state energy and a separate calculation on excited state energy and calculate the difference between them and get excitation energies as a small excitation energies as a difference between two large numbers. From the response function we get directly the excitation energies out, because I only have to find for which value of omega I have a singularity, and then I know this value corresponds to an excitation energy. But we actually can get more, and maybe some of you had some sort of theory, mathematics, calculus of complex functions or of rational functions, because they are, in addition to pole, there's something which is called the residuum. And the residuum is basically, I mean, when you have a pole, the function goes to infinity. But there might still be something left in that function which sort of makes sense, which is not infinite. And that's called the residuum. And you get that if I have a function, let's take some function f of x, and let's say that is a divided by b minus x. Obviously, if x goes to b, that function has a singularity. It goes to infinity. But I might still find out what is sort of in that singularity, in that infinite value, is there some finite, meaningful leftover called the residuum. And you do that if you if you multiply x minus b, or no, b minus x times the function, and then you take the limit of that for x towards to b. So you take the value at which your function goes to infinity, it has a pole, multiply that on the function, and then let it go to 0. And you can see that gives you a, which is a finite, and that's called the residuum. We can also do that here. So if we take the limit of h bar omega towards to one of the excitation energies, En minus E0 of our response function, but we multiply it with h bar omega minus En plus E0 of our response function omega. If I do that here, then I get, like over there, I get the numerator. Now here I have a sum over different n's, and I get the numerator for that n, and that is I get these product of matrix elements. But what is that? What is one of those? Jack?
Transition dipole moment.
That's the transition dipole moment. So if I look at the alpha-alpha component, so what I do get the absolute square of the transition dipole moment. So from the poles I get the excitation energies, from the singularities I get the excitation energy, from the residue at each pole I get the corresponding transition dipole moment, or the square of the transition dipole moment. So I get all the information which I need for the spectrum. Because the transition dipole moment is directly related to the intensity, or the other way around, the intensity is directly related to the transition dipole moment, and the position of the peak, and that means the height of the peak, and the position of the peak is obviously given by the frequency. So I can get the UV vis spectrum of a molecule from the response functions by looking at the poles and the corresponding residues. Sorry. So I get my spectrum from that.